So hello everyone, welcome to IGC Gate Coaching. So here we will be discussing about our course Gate Electrical Online Coaching by IGC Bangalore. So IGC provide offline coaching in Bangalore from last 3 years, and this year after lockdown we have moved to online platform, and now we are available across India. Anyone who want to join our classes, and classes has been taken smoothly on online platform from around April month onward for our existing students who joined us as an offline student, and then we had another set of students in May month. So here we are going to discuss about our July batch, and the duration of July batch is 6 month duration. So the timings are like this. We take classes both on weekdays and weekends. Weekdays for July we'll be taking 3 days classes, like from Tuesday to Thursday in night 9:30 to 11:30 p.m. Why we chose this night time, considering many factors? Some are working people, some are college people, and evening time is not good to have classes like from 6 to 9 something, like internet issues, or some people may have many other work. So we decided to take a slot 9:30 to 11:30 where all are free, including our team members, so we can have a peaceful classes without any disruption. And night, there will be a complete silence in surrounding, so that's a good time to learn, and even it is not that late, because many of us has habit to stay awake late night. Then Saturday class is designed in evening time. It's like 2 to 7 p.m. or 2:30 to 7 p.m. So there are two slots. One is like 2:30 to 4:30. Then there is half an hour gap, and then another class like 5 to 7 p.m. Then we have Sunday class, which happens in morning time. So again, there are two slots like 9:30 to 11:30 a.m. and then 12 to 2 p.m. Okay, so these are the teaching hours we will be teaching, and every week we'll be teaching around 16 hours, and monthly is around 70 hours, and in 6 months we'll be teaching around 450 plus hours. Now weekdays classes will be shifted to Saturday timings if it is a public holidays, and here on from August month there are multiple public holidays. So in public holidays we will take class like Saturday timing, and we will increase number of hours so we can teach more. And electrical syllabus is vast, and it is almost 1.6 times of GATE electronic syllabus, because you have to study almost all basic EC subjects, and then you have core subjects like from instrumentation, machine is a huge subject, then power electronics, power system. Though power electronics is a bit smaller, but power system again a good subject, and it has quite significant amount of syllabus. So course duration, as I mentioned, it's a 6 month, because now we are in July, and usually exam happens in February, but as of now still it is planned in February, but we are going through pandemic time, so there may be some shifting of timing. That will be other advantage with us. We can do more for you guys, considering more time. And in January, since now we are on online platform, there will be doubt classes, regular doubt classes. Previously, there was no class in January month at IGC, only online exams were going on. Okay, till December we complete everything, and then after November there will be problem practice classes, those subjects which we have already taken. So that was the course plan when we were having offline classes. Now we will be covering all subjects, including basic EC subject, then core electrical subjects, engineering, mathematics, aptitude, and how we will go about all these subjects, that I will explain in coming slides. And the course features here at IGC classes are live interactive classes, and it's like two-way classes, not one way. You will also allowed to speak as and when required. Of course, you can write your doubt in chat box also, like a big platform uses only chat box, but here you can clarify your doubt in between classes through audio as well. And for classes, IGC has its own platform like any other big institute. Okay, since this session is through Cisco WebEx, because here it's easy to join by anyone, and for our own online platform you have to do sign up and then sign in. It's like much more interesting. Okay. Now apart from classes like where we cover each and every subjects, either it is a technical or non-technical, we also provide study material in e-form. Okay. uh, Sorry. And we will be providing study material for every subject, and we have shared the link for those sample study material as well with you guys. Then we also have topic wise assignments for self practice. You guys can do using our assignments practice part. And we have weekly online exams. Okay. Exams are taken on our student portal. Okay. And exams like whatever topic we cover, there is exam for that till November, and then in December we have subject wise exam, and January we take full syllabus exam. Apart from these classes, we will also have doubt classes regularly now, either on Monday or Friday. Whatever assignment discussion we can do there. Okay, and fee for this course is 25K. Some concession is applicable here. One year means it's a GATE 2021. 2 year means GATE 2022. And apart from that, you guys will also get references books like for engineering, mathematics, aptitude, or other technical books also you will get in e-form. We have some sorts sets of books available with us which we share, and always our team member will recommend you guys which book to refer for which subject. So you guys must refer apart from NPTEL lectures as well, and we also have our internal study material for SAM. Now after this course, you guys have any concern or doubt? Ayaz or Govind, about this course features, course detail?
No, as of now, no
Okay.
concern.
Yeah. Ayaj? Okay. If not, let's move to next. So it's about our team member. So you can see even we have taught less number of people in last 2 years, considering a new entity in Bangalore. But our feedback was always best. You guys can always check feedback or review about IGC GATE coaching in Bangalore. And for even less students, like 10 to 15 students also, we have provided faculty for each and every subject. And last 2 years we have taught 100% syllabus. Okay, and we have been teaching consistently 10 to 15 students. Okay, in last 2 years. This year also our projection will be more of same. We are not worried about more students. Okay, so here the network is taken by Mr. Prashant, and also our V Raghuram sir also expert in network theory. And for you guys, network theory will be taken by V Raghuram sir, and he's from IIT Bombay. Then signal system is taken by Mr. Mukesh, is from IIT KGP. Mr. Dheeraj take care of analog system, is from IIT Bombay. Siva sir will give cover your EMT basics part, and he's from CSIR lab, and he's also working in Bangalore in one of government organization. Mr. Arnab, he's from ISC Bangalore. He was under 50 ranker in GATE Electrical. He work in one of the MNC, and he take care of instruments and measurements. Also, he's expert in control system. Mr. Ramashankar, he will be available today, and he is expert in electrical machine and power electronics. Uh, And then we have Mr. Adip. He's also from ISC Bangalore. He will be taking care of power system part. Then we have another subject like digital electronics. So for that we have Mr. Prashant also, and we have Mr. Vijay also. Mr. Vijay also has multiple expertise. He's from NIT Calicut. And now mathematics part will be taken care by Mr. Karthik. He's from ISC Bangalore, and he's from CSC background, is a dedicated faculty for GATE CSC as well as mathematics part. And aptitude will be covered by Mr. Siva Kant. He's from IIT Roorkee BTech, and he was a Times faculty earlier. So this is about our whole team to cover, whole syllabus of GATE electrical engineering. So any concern here?
No.
Yes, Govind.
No concern.
Okay, thanks. And the good thing, you will find all these member will be connected with you guys through our online media, where you can guys as many as doubt. That is not possible by many big institute, and these all people are topper of their own time. So there is a lot to learn from these guys to do best. Now come to GATE electrical engineering syllabus part. Now here, GATE electrical engineering syllabus is divided, I think, in 9 or 10 sections. So the first section is engineering mathematics, and it's a we club with aptitude. So the engineering mathematics plus aptitude has a weightage of around 25 marks plus. Mathematics is like vary between 10 to 15 marks, and it has several topics. Though the weightage is little less from mathematics, but syllabus is more, and so it takes us like 50 plus hours to cover this complete mathematics part in proper way. But this mathematics has lot many application in basic EC subjects like signal system, or if you take analog or any other subject. Okay, so and also in electrical machine, where basic calculus and other things are very much required. And aptitude is like syllabus is like till 12th standard what you have learned in basic mathematics, and then verbal English part. So at our institute we only cover numerical aptitude part, and for this verbal part we provide references for self practice. We do not teach English part here. Now come to another subjects, like section 2 is a electrical circuit, which is again network theory part. Then we have electromagnetic field, EMT basics also, then signal and system. So these three subjects where the weightage is more from signal system and electrical circuit part, having total weightage 15 to 20 marks. EMT also some basic questions they ask, like around 4 marks sometime. Now the come to core subjects, we have electrical machine, then power system, and again basic EC subject, control system. So these three subjects is having almost highest weightage in GATE electrical engineering syllabus, and which is close to 30 to 35 marks, where machine will be close to 15 marks, and then power system and control system questions like 10 marks or. Then next section is what, like a small part is what electrical and electronic measurement, which has only 2 to 4 marks of weightage. And then analog is another good subject which has close to 5 to 10 marks of weightage. And then power electronics also, comparatively power system and electrical machine, it's a small subject and has weightage of close to 5 to 10 marks again. So this is about whole GATE electrical engineering syllabus part. Okay, and we take care of almost each and every topic at our place at IGC. And there are people, multiple people to teach multiple subjects. Okay. Now, how we are going to go through syllabus in this 6 month of course duration? So we will be starting from this July month, three subjects: network theory, instrument and measurement, and EMT basic. And then once like a few of the subjects like this network theory takes little time, but instruments and measurement and EMT basics will take lesser time. So we will move to next sets of subjects like electrical machine, signal system, and mathematics. Okay. And then once like we complete machine, which is a huge subjects, we have to teach close to 60 hours for that same. And signal and mathematics again will take more time. So we run like this August and September these subjects, and then in October we are going to start control system and power electronics. And in November November we will be teaching power system and digital EC. Here by mistake I have written CSE, it's a digital electronics. And in December we will be teaching aptitude and whatever the pending part of power system and digital electronics with that. So this is about almost 100% syllabus of GATE electrical and our plan to cover in the way we do. Now, these are the source of study material, sample assignment, sample online exam, sample videos. We are keep sharing, some sample videos on YouTube. Okay. So have you guys gone through this sample material, sample assignment, sample online exams, and sample videos?
No, till now I have
Uh,
not gone through.
you didn't get, but I have shared the link for Sam. Ayaz, did you go through this? Okay, so how you find it so effective? Uh, that you guys can share always concern or doubt or any improvement as well. Okay. Yeah, Govind, you want to say something?
No.
Okay, all right. Okay. So now let's move to last part. Okay. I will show all these also in today's this session in my part. So these are the few toppers achievers in last 2 years. This is 2020 achievers. So the best gate score in 2020 we got around 656, and we have people mostly all are working people in Bangalore. That's why you can see the college name from different colleges. We are in Marathali, Bangalore, which is close to Whitefield area where almost every MNC situated. Okay, so people from those places, they want to pursue their further interest in core instead of working in IT companies, so they join us for classes. And then in 2019 you can see again the best gate score from us was 772 and he was the rank 341. And these are the other gate scores. Now, these are the contact details about IGC. So we are available on this number. These are our mail IDs. This is our website. Of course, we have very good presence in on Google. Okay, we are one of the top rank in a small institute. If you check in Alexa or any place, then we have a good presence on social media as well. You can see our FB page or YouTube. We are making presence from last 2 years, last 2 months. We didn't focus earlier much on YouTube part. We are also present on Twitter, Instagram, LinkedIn. Okay. Now the location, offline class location is in Bangalore in Marathali, and we take classes at college called Hindustan College. Okay, on weekends and public holidays. This year, no offline classes due to this COVID-19. And our office is situated in Bangalore. It's also close to Marathali. There is area called Pannatur where we are situated. So this is all about IGC. So thank you guys on this introduction part. And if you guys have any concern from here, let me know. And then I will move to the next part where I will show you guys all our sample steps. Yeah, any concern? You guys can write in chat box, yes or no. Okay. So so this is IGC website, iitiansgateclasses website. So you guys can always visit our website. Okay, and here you can find each and every detail, what we do, how we do. Okay, either it is our course details, our team member details, or any other details. Okay, so we maintain utmost transparency in what we do, who we are, how we do. So here you can see the links. This is gate class schedule. So if you click here, you can see the class schedule of each week. Okay, whatever classes we are taking. Currently, we have a batch 1 and batch 2 kind of things, and there you can see which subjects are going on, who is teaching, what is the timing. It's all available, and it's available from almost last 2 years plus from when we started these EC electrical branches. And at IGC currently we are having 6 branches of engineering. We started basically this institute as a Gate Aerospace Institute, then we moved to mechanical, then we started electrical and electronics. This year we have started Gate CSE and Gate instrumentation. But whenever we started as a team, okay, and we are delivering very well whatever we promise. Okay, and even with a small number of students also we are happy to teach well. Okay, and here one thing we maintain is a quality. Yeah, yes, you want to ask something? Okay, so let's move to next part. Okay, so I'll move to next step. Okay, one moment here. Yeah, so this is what sample assignments by IGC. So this is one assignments for power electronics. You can see these are the questions, and uh, so these questions are for self practice. Like whatever topic we teach, we keep assignments for practice. And if you guys consistently, practicing assignments with the previous year's paper, there is no doubt in securing a good gate score. Okay, so this is about assignments. So Govind, you can go through this. And then we have study material also. So this is how our study materials looks like. This is one of the study material for power system. So we have given about all the topics of power system. It will include like derivation as well as theory part, and it is for every subject in E form. Then another aspect is what very important, mock exam. So for mock exam, we have our own tool. I'll just go to that as well. One moment. Yeah, so you can see this is a IGC online test series portal. So once you guys join, we will provide credential to log in this. And here you can see there are exams available. You can see this is a power electronics exam. This is the topic wise exam one. This is two. You can see aptitude exam, digital electronics exam. You can see the mathematics exam, and you can see signal system exam. These all are topic wise exam. You can see the hello sir. I will hand over in few minutes, sir.
Okay, sir. Okay.
Yeah. So this is what I was discussing about IGC, online exams, and which we observe not many institute provide proper topic-wise exam. Okay, which is what we got. There are many exams where, like, people will just put full syllabus exam, and that too from particular topic only they take questions. But here, we have proper sequence of exams which start with subject-wise, topic-wise, and then you can see here we can filter out particular subjects exam. So just take the digital electronics and you will see all the digital electronics exam, because we have already taught this subject for our February batch. You can see the network circuit exam. So there are multiple exam for network circuit, and so this is about our online exam. Okay, so as I mentioned, the classes will be through our IGC portal. Okay, and now I will hand over to our Ramashankar sir. So, sir, I will provide you presenter, and you can start. Okay, so thank you guys, and let me know if any concern for whatever we have discussed.
Hello.
Yeah,
Hello.
you are, yeah,
Yeah.
audible, sir.
Yeah, sir. I just let me share the screen.
Yeah, sure, sir, sure, sir.
So can you see my screen, sir?
Yeah, yeah, I can see, sir.
Yeah. Okay. Hi guys. Myself Shankar. Today we'll be seeing some of the power electronics basics. So may I know you like? Can you give some introduction about yourself? Like, hello.
Yeah. Yeah. So I am Govind Mishra. Actually, I am working in IT software field. Actually, I have done BTech in electrical engineering. So I thought I'll try some get exam if I
Yeah.
can secure some good score and can get a job
Okay.
easily.
Okay. Yeah. So any other? Only one. Do you know Govind? One more guy is there, right? Hello. Hello.
Yeah, yes, he is writing in chat box.
Yeah. Sir, should we wait or should we go ahead? Hello.
Yes, sir, go ahead.
Okay, sir. Okay. So today we'll be seeing some of the power electronics basics. So first of all, we'll start with the what are the topics we'll be having. So basically, we have six major topics. The first topic is the basics of power electronics. Here we'll be dealing with type of switches like SER and some of the basic elements like RLC. And the next topic we have is a rectifier circuits. Here we will be dealing with single phase and three phase rectifier circuits with the different load configurations like RL, R load, RLA load configurations. In the next topic, we will be having a DC-DC converters. Here we will be talking about the three major converters mostly, uh, the boost converter, the buck converter, and the buck boost converter. Okay. And the next topic we have inverter circuits. So here we'll deal about two major circuits. One is the single phase and three phase inverter circuits. After that, we'll be covering some of the control techniques for inverters, such as PWM techniques. And the next topic we have AC voltage regulators and cycloconverters. Actually, these are two different topics. So the AC voltage regulators use it to control the output voltage, whereas the cycloconverters are used to control the output frequency. Next, we have a commutation circuits. So commutation is nothing but the turn-off process of SCR. So actually, we will be seeing what are the different type of commutation circuits available to turn off the SCR. So next, so what does power electronics means? Power electronics is nothing but a technology which is associated with efficient conversion and control of power using power semiconductor devices. Generally, semiconductor devices are of two types. One is device level, that is also called as signal level. The other one is a power level. So in case of signal level, the power is in the range of milliwatts to watts, whereas in the power level, the power is in the range of watts to megawatts. So in power electronics, we'll be dealing with this kind of devices, power level semiconductor devices. So the next, we'll be seeing some of the applications of power electronics. So there are several applications of power electronics. So first we'll start with the drives. Drives. So in case of drives, we have both AC drives as well as the DC drives. So let us have a look at the DC drives. Say speed control of a DC machine. So for a DC machine, we know that induced EMF can be given as is equal to phi Zn by 60 into P by A, right? Where phi is a flux, Z number of conductors, N is in RPM speed, A is a parallel path, P is a number of poles. So we also know that E can also be written as Vt minus Ia Ra, right? Ia is armature current and Ra is the armature resistance. Vt is the terminal voltage. So by substituting E in the above equation, we can write N as N proportional to, like neglecting the constants, we can write N is equal to Vt minus Ia Ra by nothing but flux, right? So flux generally is proportional to current, that is shunt field current. We can also write shunt field current as terminal voltage by shunt field resistance, right? So we can write this as Vt by Rf. So this is the basic formula for the speed. Now if you want to control the speed n, so what we can do is we need to add an external resistance in either in the armature circuit path or in the field resistance path. So the corresponding methods are called armature resistance control one method. Other one is the field resistance control method. Okay. So give me a minute. I'll erase this. Okay. So suppose by incorporating these two methods like armature resistance control method and field resistance control method, we can write N equal to Vt minus Ia into Ra plus some external resistance in the armature path. We call it as say Ra1. Okay. This is equal to N is proportional to. Okay. This is nothing but Vt by field resistance plus some external resistance in the field resistance path. We call it as Rf1. So now N can be varied by varying Ra1 or by varying Rf1. But the problem here is this kind of method or control method is an inefficient method because most of the power loss takes place in the resistors in the form of a heat. So this is not a what you call efficient method to control the speed of motor. So what is the other way we can control the speed of a motor? So we can also control the speed by varying terminal voltage Vt, right? So but generally the terminal voltage is nothing but the supply voltage, which is a fixed supply. But we need some variable supply. So how we can achieve this? So we can achieve this by using a paratronic circuit. Suppose here we have a DC voltage and here I am connecting some paratronic converter. Okay, this is we call it as VDC. And here we have VT. This is nothing but the terminal voltage. This is some power electronic converter. So using this power electronic converter, general power electronic converter consists of switches. So we need to give the control signal for these switches. So based on this control, we can vary Vt, which means we can control the speed by varying the Vt. So in this kind of method, the power taken from the source is not a fixed because for low Vt, the power drawn from the supply will be less. Similarly, for low speeds, the power drawn from the source is, which means for low speeds, the power requirement or taken from the source is less. Similarly, for high speeds, power taken from the source is more. So, which means this method is the most efficient way of speed controlling. So okay. So what could be this power electronic converter? So it can be a DC-DC converter. So we'll be discussing about this in the later stages. Okay. So from this example, we can realize that using power electronics, we can control the power effectively. Like what do you mean? With less losses. So next we will be seeing another application of power electronics that is called the power system application. Power system application. So in power system also we have several applications for power electronics. However, we'll discuss one application. One is called as a reactive power compensation. Reactive power compensation. Okay. But that is nothing but the Q compensation. Okay. So what is the reactive power compensation? Suppose here we have a grid and is connected to some transmission line, and then we have the bus of voltage V, and here we are connecting a load. Okay. Suppose this terminal voltage V depends upon the amount of reactive power drawn by this load, because we know that V proportional to Q. Right. So when this load draws the more Q, V drops, right? So to improve this voltage profile, what we have to do is we have to supply the reactive power Q required by the load QL locally, means within this range. So for this, what we do is we'll connect a capacitor banks at the load end. This is the V, this is the load. We'll be connecting a capacitor bank here. So this capacitor bank will supply the Q required by the load, right? So in this way, we can improve the V. But the problem here is, suppose if the load is further increased, which means the Q drawn by load is also increased. In that case, V decreases further. In general, the reactive power supplied by capacitor is given by QC equal to V square by XC. So V is decreasing, so the capacitor Q supplied by Q capacitor bank will also be decreasing. So, but actually we want capacitor bank to supply more Q, because since the load is drawing more Q from the grid, it has to be compensated by the capacitor bank. So since the load reactive power is increasing, the capacitor bank is also has to supply the increased load reactive power. So, but with this kind of arrangement, what is happening is QC is not increasing, QC is decreasing. So this will further deteriorate the V profile. So how can we overcome this? So that's where the power electronics comes into picture. So suppose if I modify this circuit, including some power electronic converters here. This is the bus, and here we have the load. And here I am connecting some power electronic converter. And then I am connecting the capacitor. Okay. Now this voltage we call it as say VR. Okay. VR. Okay. In this case, QC can be given as VR square by XC, right? So in this case, even if V decreases, using this power electronic converter, we can control VR in such a way that even if V decreases, we can switch this power electronic converter such that VR increases, which means QC is increasing. So even if the load is increased, the QC is able to meet the increased load reactive. Now the example of the power electronic converters. Uh, so till here, are you clear? Do you have any doubts? Hello. Hello. Hello, Govind. Hello, Govind.
Hello.
Okay. Then
Yeah.
I think you are clear. Yeah, yeah. Is it clear till now? Do you have any doubts?
Yeah.
Okay, okay. Then I'll proceed further. what are the other applications of power electronics? So we'll be having some other applications like renewable energy integration, that is PV and solar. PV, nothing but solar and wind integration. And similarly, we also have other applications like automobiles, like electric vehicles. And we also use it in HVDC transmission. And also we have some domestic applications. Okay. So these are some of the applications of the power electronics. So next we'll be seeing what are the advantages and disadvantages of these power electronic circuits. So from the earlier example, we realized that using power electronics, efficient conversion of power is possible, right? Which means less losses. This also means the heat generated from the circuit is less. Hence, the size of heat sink will reduce. So this results in reduced size of circuit, or what we can say reduced size of or smaller equipment, right? So using smaller equipment, we are achieving a efficient power conversion. That is advantage. So what is the disadvantage? Disadvantage is one of the major disadvantages is harmonics. So due to the switching phenomena, there will be harmonics generated. Suppose if it is a rectifier, we have a ripple on the source side, and if we have an inverter, we'll be having a harmonics on the load side. So these harmonics causes a lot of problems. So we have to overcome these harmonics. So how can we overcome these harmonics? So in the rectifier circuit, suppose in the rectifier circuits, we call it as a ripple, and in the inverter circuits, we'll call it as a harmonics. So in inverter circuits, we'll be using PWM techniques. Circuits, we'll be using source inductance, effect of source inductance. However, I'll cover those topics in the next lecture. Okay. So we'll go to the next slide. So the applications which we have seen till now are most of them are high power and low frequency applications. So the other important elements or the important elements in any power electronic circuit are switches. So what are the operating modes of a switch? One is the on state, other one is the off state. So if you see this figure, this one is the off state, and this one is the on state. So when switch is on, ISW equal to some finite current, and switch is off, ISW equal to 0, right? So ISW equal to some finite current, or it can also be infinity. Suppose, yeah. So this leads to another classification of switch called ideal switch and practical switch. Suppose if it is a practical switch, when switch is on, it will carry a finite amount of current. If it is an ideal switch, it can carry infinite amount of current, right? So we'll be seeing what is the basic difference between ideal switches and the practical switch. So ideal switch will be having a zero conduction and zero blocking losses. What are conduction and blocking losses? So conduction losses are associated with when the switch is in on state, whereas the blocking losses are associated when the switch is in off state. So if we have an ideal switch, it will be having a zero conduction as well as a zero blocking losses. Whereas for the practical switch, it will be having a finite conduction and finite blocking losses. The next point is actually for changing the switch from this is the off state, right, to off state to on state or vice versa can be done instantaneously in an ideal switch. Means it does. Whereas in a practical switch, it takes finite amount of time, like what you can call, if you take an SCR, we have a turn on time, right? Turn on time. Similarly, So it will be taking finite amount of time for switch to change from one state to another state. So the other difference is for ideal switches doesn't require any external to turn on or turn off or to maintain a given state. Whereas a practical switch, it requires an external source. So what does it mean? For example, if you take an SCR, so SCR can't be turned on like that, right? Once we connect SCR in a circuit, it won't be turned on like that. So we have to give some pulse, right, to turn on. So we require an external source, what is called a pulse circuit, so which gives a pulse. Then the SCR can be turned on. Similar like BJT or IGBT, it all requires an external circuit, right? So this is the some of the basic differences between ideal switches and the practical switch. Hello. Yeah, Govind.
Yes.
So this is okay, right? This one is clear for you. The classification.
Yeah, this is clear. Actually, as I'm working in software from last 2 years, I have so I have to study the basics again to understand.
It's okay. If you have any doubt, you just ask me. It's okay. If you didn't understand anywhere, you just stop me there. So this is
Okay.
okay, right? You don't have any doubts here.
Yeah, switches are clear.
Yeah. Okay, then we'll go to the next slide. Okay. What are the other important elements in a power electronic circuits? Apart from switches, we will be having resistors, we'll be having inductors, we'll be having a capacitor. So for the resistor, the relationship is linear between, it's like V is equal to IR, right? So it is a linear relationship. Whereas for inductors and capacitor, this relationship doesn't hold. Actually, mostly it depends upon the circuit conditions. So what does the circuit condition means? It means like suppose if the capacitor is initially charged, or how the circuit is arranged, or what other components are there in the circuit. These all includes the circuit conditions. So if you see, so for a resistor, VR can be written as R into IR, right? So V is nothing but I into R. For inductor, we can write V is equal to L di by dt, which is not a linear relationship. And similarly for capacitor, we can write I equal to C dV by dt. This is also a non-linear relationship. So the next question is, generally inductors doesn't allow the sudden changes in current. So why is it that? So why is because suppose if you see this equation from this equation V is equal to L di by dt, if there is a sudden change in current, then V becomes infinity, which is not possible practically, right? So that's why inductor doesn't allow the sudden changes in current. Similarly, for capacitor also it doesn't allow sudden changes in voltage. Why? Because similarly, if the voltage changes suddenly, the capacitor current becomes infinity. This is also not possible practically. So that's the reason why capacitor doesn't allow the sudden changes in voltage. So, Govind.
Yes.
So these are the basic
Yeah.
elements.
Yes, I
Okay.
understood
Next
this
will
one.
be okay. Next we'll see some rectifier circuits using these elements. Okay. So what does a rectifier circuit mean? So rectifier circuits are used to convert AC power to DC power. Okay. So what are the applications of rectifiers? We use applications of rectifier like in battery chargers. Battery chargers, like suppose in house we have an UPS, right? UPS have a battery. So to charge this battery, we have to convert the supply, AC supply into the DC. There we use the rectifier circuit. The other application is speed control of DC motors. Similarly, in HVDC transmission, we'll be having two converters. One will be converting DC to the AC, other one will be converting AC to the DC. So these are the some of the major examples of the rectifier. There will be other examples also. So next we will be seeing the rectifier classification. Uh, so generally rectifier circuits are classified into two types. One is a circuits and a single phase circuit. So within single phase circuit, three type of converters like controlled converters, uncontrolled, and semi-controlled. So what does this mean? Controlled, uncontrolled, and semi-controlled. Control. Actually, this depends upon the switch application. Suppose if you take a control converter, we'll be using SCRs, If it is uncontrolled converter, we'll be using diode. And if it is semi-controlled, then we will be using a combination of controlled and switches. For example, we have an half control converter where we'll be using SCR and diode combination. So now these converters are further classified into two types, like half wave and full wave. What does a half wave means? Half wave means, suppose, so one cycle. So one cycle is for 50 Hz, it is 20 milliseconds, right? So we'll be having, this is nothing but one cycle. So in case of half wave, we will be having one waveform per one cycle. This is one cycle. So we'll be having one to half portion. There won't be any this portion. This is nothing but one waveform per cycle. That is half wave. In case of full wave, we'll be having two waveforms. Maybe like this. This is one cycle, and we'll be having two waveforms. This is called as a full wave. Okay. Yeah. Govind, are you clear with the classification?
Yes. So I want to know what is the controlled and uncontrolled.
Yeah, controlled and uncontrolled actually. Controlled and uncontrolled is like it's a switch classification. Suppose if you take the control where we use an SCR, right? SCR is a control switch because we use a pulse, right? We use gate pulse to turn on the SCR, right? Whereas in case of
Okay.
uncontrolled, we are using diode, right? Diode doesn't require any gate pulse, right?
Okay.
So it just suppose if you take a diode, say this is the diode. Wait, I'll draw it neatly. In case of a diode, if we apply positive here, if we apply negative here, the diode will get turned on, right? There is no need to give the gate pulse. Am I clear?
Yes, yes. So we can't control the turn on, turn
Yeah,
off the
yeah.
diode.
But if you have an SCR, even if you give the positive and negative here, we need to give some pulse here, right? To turn on the
Mm-hmm.
SCR.
Yes,
So
yes.
that means the on state of the SCR can be controlled by giving pulse. So that's why it is called as a controlled. And this is called uncontrolled. Is it clear now? Hello, Govind?
Yes, yes, clear now.
Okay, I will be going to the next slide. Okay. So we'll be seeing one rectifier circuit that is called as a single phase half wave rectifier circuit. So how the circuit diagram will be? So here we have an AC source. This is the AC source, and this is the switch. Actually, I just drawn it like this because I don't want to go much deeper, like what kind of switch we are using. All these things I don't want to discuss. I will be discussing in the next class. So I just for time being, you just assume it is a switch. So if you give the okay.
Okay.
And yeah, this side we have the load, and the load current is I out, and the load voltage is V naught. And the input we have a sinusoidal voltage with peak value is Vp. So now we'll consider the load is of a resistive type. Say the load is a resistor load. Okay. So we'll be seeing more the waveform. See. This is the positive during the this is the supply voltage, right? Which is the sinusoidal voltage for one cycle, right? This is one cycle. This is pi. This is 2 pi. Now what we are doing is, let us assume that this switch is an uncontrolled switch. Say it's a diode. So what will happen is for diode during the positive half cycle, the switch will get turned on, right? And during the negative half cycle, the switch will be turned off. So when the switch is on, the output voltage, which is output voltage, is nothing but it is equal to the input voltage, right? Because both are in parallel. So during the positive half cycle, output follows the input, right? And during the negative half cycle, the switch is open because the diode is reverse biased. So the output voltage is 0. Okay. Since it is a resistive load, we know that the relationship between V out or I out is linear, right? They are proportional. So this
Okay.
also follows the same pattern but with a reduced magnitude because we know that I naught equal to V out by R. Okay. So actually here these waveforms are instantaneous waveforms. Okay, these are not the average waveforms. These are instantaneous waveforms. What I mean is, it is nothing but V out of t or omega t. It is varying with. If you want to find an average of any signal, we have a formula, right? What is that? Suppose I want to find the average of function f. F average can be written as 1 by t integral 0 to t f of t dt. Okay. So if I want to find the average value of this waveform, this output voltage, so how I am going to write this equation? So average is nothing but V out, which is equal to 1 by 2 pi, because for one cycle, right? Integral 0 to pi, only pi, because during the positive half cycle only we have the waveform, and the negative half cycle it is 0. So that's why it is pi. What is f of t? F of t is nothing but V peak sine omega t d omega t, right? So we'll do the integration. So that is equal to Vp. If you take it outside, Vp by 2 pi. So what is integration of sine omega t? It's nothing but minus cos omega t 0 to pi, right? So if we substitute that, what we'll be getting? Vp by 2 pi into 2, right? That is nothing but Vp by pi. So this is the average value of output voltage. Similarly, the average value of output current I out equal to V out by R. So that is equal to Vp by R into pi. Okay. So here we have one more parameter. We call it as gamma SW. This is nothing but gamma SW is nothing but it is called as conduction angle. So what does conduction angle mean? It means for how much duration the switch SW is conducting or SW is turned on. So if you see this waveform, the SW is turned on for a duration of pi, right? So gamma SW is equal to pi, which is nothing but 180 degrees. And there is one more term called as PIV, peak inverse voltage. What does it mean? It means the maximum negative voltage that can be applied across this switch. Okay, suppose if you take the switch voltage, this is positive and negative. So when the switch is on, this voltage is 0, right? Similarly, when switch is off, VSW is nothing but minus VT, right? If you do both are will be in the parallel, right? So nothing but the source voltage. In this case, the maximum value of the source voltage is nothing but this one, VP, right? So the PAV is nothing but VP for this circuit configuration. Are you clear, Govind? Do you have any doubt in this circuit?
Uh, Not totally clear, but I will go through this.
No, you can ask me. I'll explain. We have a lot of time to discuss. Where you are not clear, I will explain again.
Uh, so you told that in the voltage in the uh, for for the negative half it will not be the here you can see there are two cycles are going in the voltage.
Yes, yes. So, see, you're saying why it is called half wave, you're saying? Hello.
I try to read something more easily. I think I forgot. I will read to get things.
Okay. It's okay. Okay. So there is one more derivation. Actually, we have seen average voltage rate, which is we called as V out. How much we got? We got Vp by pi, right? Suppose if you want to find the RMS voltage, that we call it as VOR. Suppose if I want to find the RMS voltage of a function f, say f of t. So how can we write? That is equal to one by t integral 0 to t f square of t dt square root. This gives the RMS value of the function f of t. So Similarly, if you want to find RMS value of output voltage, we can write V naught. Suppose I'm squaring for time. Okay, so VR square equal to 1 by 2 pi, because for one cycle, and 0 to pi because we have an output voltage only for a duration of pi, into Vp square sine square omega t d omega t. This is nothing but f square, right? So if we do this derivation further, so we can take Vp square outside, Vp square by 2 pi integral 0 to pi. So how can we write a sine square omega t? We can write it as 1 minus cos 2 omega t by 2 into d omega t, right? So if you do this further, Vp square by 2 pi 1 by t 2 pi minus 0 minus 1 by 2. If we do the integration of cos omega t, we'll be getting cos 2 omega t, we'll be getting sine 2 omega t by 2, right? So it will be sine 2 omega t by 2 is 0 to pi. So this is equal to Vp square by 2 pi pi by 2 minus 1/4 into sine 2 pi minus sine 0. So this gives Vp square by 4. So this term is 0, and this pi cancel, will be getting Vp square by 4 VOR square. Now if you take squaring square root, VOR can be written as Vp by 2. So this is called RMS value of output voltage. Govind, are you clear with this derivation? Yeah, any doubts here?
Yeah, I'm clear.
Okay. So this is for the R. For the R load. This is for a resistive load. Okay. Now we'll see the same circuit. We'll be changing the load in the next configuration. So suppose, so we'll see a same circuit, single phase half wave rectifier. We'll be seeing a inductive load. So we'll be seeing an inductive load. So how inductive load will work? So for an inductor, in this case, we can write, suppose if the switch is on, let us consider if the switch is on. Okay, if the switch is on, we can write V out, say V out is nothing but Vs supply, right? So V out can be written as, since it is an inductive load, we can write LDI out by dt equal to Vp sin omega t, right? So now I'll take the inductor the other side, di naught by dt equal to Vp by L sin omega t, right? So now what we do is we take integration, or we do integration on both sides. So if we do integration on both sides, what we're going to get? So we'll be getting I naught equal to 1 by L integral so we'll do it further. I naught equal to Vp by L. If we do integration of sine omega t, we'll be getting minus cos omega t by omega plus some constant. This constant is because of initial conditions. Okay. So initial condition is nothing but, so whether the inductor doesn't have any initial charge, which means initially it is carrying some current or not. So let us assume the initial current carried by inductor is 0, yet time omega t equal to 0. Okay. So if we substitute this in this above equation, we will get the value for k. So we will be getting, how much we will be getting? I naught is 0. So we will be getting Vp by omega L. Cos 0 is nothing but 1. We have minus, so plus k, right? So k is nothing but Vp by omega L. Now use the value of k in this equation. So that gives the full-fledged formula for I naught. So I naught equal to minus Vp by omega L cos omega t plus Vp by omega L. Okay. Now we take Vp by omega L common. So Vp by omega L into 1 minus cos omega t is the expression for I naught. So if we plot this I naught, how does it look? It is nothing but the cosine wave, but we subtracted from 1. Suppose omega t is 0, then cos omega t equal to 1. So 1 minus 1, it will be 0. Similarly, we will plot for pi and 2 pi. We take pi by 2, right? Similarly, if omega t equal to pi by 2, cos pi by 2 is 0 and 1 minus 0 is 1. So it will be coming, say this is 1. So it will come here, right? Again, pi it will be 0. No. Just, yeah. So similarly at pi, how much will be getting? Cos. So if you plot this waveform, it will look something like this. At 2 pi, cos 2 pi is 1. So 1 minus 1, it will be 0. And pi, it is getting a maximum value of 1. Right? So if we go back here, so I out is something like this. So which means for the entire 2 pi duration, the switch SW is conducting, right? So since the entire duration switch is conducting, which means the switch is turned on. In that case, the output voltage is nothing but the supply voltage. So the output voltage will be same as the input voltage. That is nothing but this one, right? Govind?
Yes.
So are you clear how we got these waveforms?
Yes. I clear.
Yeah. So the next step is we have to find the average values of these waveforms, right? So we have to find the average value of output voltage. That is nothing but V out and I out, right? So if you see this waveform, this is nothing but a sinusoidal waveform where we have a positive half cycle and negative half cycle of equal area, right? So if you do averaging, it will become 0, right? Similarly for I naught is nothing but the average value. We have to do averaging. It's nothing but 1 by t integral 0 to t I out of t dt, right? So we'll be seeing that here. So you can write average value of output current I naught equal to 1 by 2 pi, because it is conducting for the entire duration, like I mean one cycle, and here it will be 0 to 2 pi, not the pi. In the earlier case, for the entire cycle, only for pi duration the inductor is the resistive load is conducting, right? So but here for the 2 pi duration the switch is turned on, so we have to take 0 to 2 pi I naught d over the expression for I naught here, right? So if we substitute that here, 1 by 2 pi integral 0 to 2 pi Vp by omega L 1 minus cos omega t d omega t. So this gives a final, or we can do it further also. Vp by 2 pi omega L 1 into 2 pi minus 0 integral cos is sin omega t 0 to 2 pi, right? So if we substitute this and solve, we'll be getting Vp by omega L. So this is the average value of output current. Right? So earlier we discussed that there are two important parameters, right? One is gamma switch, which is nothing but conduction time of the switch. So in this case, if you current is flowing for the entire 2 pi duration, which means the switch is on for the entire 2 pi duration. So the gamma switch here equal to 2 pi or 360 degrees, right? Whereas in the earlier case, you see the resistive load, the current is flowing only for pi duration, which means the switch is only on for pi duration. That's why gamma switch equal to 180 degrees. Right? So, Govind, are you clear with this L load, inductive load?
Yes, I'm clear.
So is the derivation is okay, or you missed something, you didn't get anything here? Can you can ask me.
Yeah, it's okay. As I told,
So
I have to go through a little bit more to
no,
get
no,
clear.
it's okay. You can go through the class. I mean, if you have any doubt, even if it is a simple doubt, also it's okay. No need to worry. You
Yeah,
just ask me. I will explain.
as I told, I have gap 2 to 3 years. I was working software engineering, so
Yeah, I
yeah,
get it.
I am not in touch with these things, so I have to study a little bit more too. But I
It's
have
okay.
studied all the things before.
Uh, okay. It's okay. Take your time. But even if you have any simple doubt, also don't hesitate. Just ask me. I'll explain. There is no
So,
need to worry. Okay.
sure. Thank you.
So the next one also will be seeing the same circuit with a different load. So the circuit diagram will be same, and then we'll be having a R plus L load. So the source is same. We'll be having the same source, that is V peak sine omega t. And here the load, which is nothing but R plus L load. So it is nothing but, so we'll be having a resistor in series with an inductor. So during the positive half cycle, say since it is a considering it as a diode, so it will be forward bias, so which means it gets turned on. So when the switch is on, so if you apply KVL, I can write this as minus V of t plus, since the current flowing is I, right? So we call it as I naught, R into I naught plus L di naught by dt, which is equal to 0, right? So if you take the source voltage, the other side, we can write the same equation. R naught plus L di naught by dt equal to V of, so that is equal to R I naught plus L di naught by dt, that is equal to Vp sine omega t. So this equation now I'll divide by R on both sides, so I'll be getting I naught plus L by R di naught by dt equal to Vp by, uh, sine omega t. So we'll continue the derivation in the next slide. Okay. So if we take inductor also, the other side, we can write I naught I naught plus 1 by tau di naught by dt equal to Vp by L sine omega t. So tau is nothing but L by R, is nothing but a time constant. Okay. So this is nothing but a first order differential equation, right? So generally for the first order differential equations of this form, the solution can be written as I naught e power t by tau equal to integral Vp by L sin omega t d power t by tau dt. dt plus some constant c. Okay. Mathematics. Uh, for the demo, I'm giving a brief explanations. But once you're what you call got experience with this, it's very easy to do these derivations. And in exam, actually, they are not going to ask these derivations. They are going to ask you the final formula. So you just have to remember that formula. Okay, go ahead.
Yes, yes.
So actually, like for understanding purpose, I'm giving you all these explanations. But actually, for the exam point of view, there is no need to remember the entire derivation. You just have to remember the final formula. Okay. So there is one more formula. Actually, this equation, this integral Vp by L sin omega t power t minus tau. This is similar to e power ax sin bx dx. Integration. This is one more integration formula. This can be written as e power ax by a square plus b square a sin bx minus b cos bx. Okay. Now this is right there, a square plus b square. I am going to split this. So this I am going to write as e power ax by square root of a square plus b square equal to a by root over a square plus b square. This is nothing but x, right? X I can write as root x into root x. So that's the same I'm doing here. So into sin bx minus b by root over a square plus b square cos bx. So this equation can be written as e power ax by root over a square plus b square sin bx minus theta. This is nothing but sin a minus b formula. If x, this is nothing but sin a minus b. If you expand this, you will be getting this. Here, where theta is nothing but theta equal to tan inverse b by a. Okay. Are you clear going till here?
Yes, yes.
Yeah. So actually, there is some more to this derivation. We'll get extend. So if we substitute this equation in the earlier equation which we got, that is I naught e power t by tau equal to integral Vp by L sin omega t e power t by tau dt plus c. We have seen that integral, this equation is in the formula of e power x integral e power x sin bx and dx, which is equal to e power ax by root a square plus b square sin dx minus theta. Okay. So if we substitute this in this expression, it will be something like this. Suppose instead of e power ax, we have e power t by tau. Instead of sin bx, we will be having sin omega t, t by l sin omega. This will come as Em by root over r square plus omega l whole square sin omega t minus theta. X is nothing but t here. Okay. So the final expression will be I naught equal to Vm by root over r square plus omega l whole square sin omega t minus theta plus some constant. So this depends. This is nothing but the initial condition. So in initial conditions, if you take say at I of 0 equal to 0 at omega t equal to 0. If we substitute this equation, we will be getting t equal to m by root over r square plus omega l whole square sin theta. So now we'll substitute this equation in this here, and then that gives the final expression for I naught, that is equal to Vm by root over r square plus omega l whole square sin omega t minus theta plus sin theta into e power minus r by l into t. Okay. Suppose if you see this equation clearly, we will be having two forms. This is, suppose this is called as the first term. We call it as first term. And this one we call it as second term. So now what I am going to do is I am going to plot this I naught. How it is going to look for plot. So first I am plotting the first term. Then next I will be plotting the second term. Then I will be plotting the resultant, which is nothing but sum. Okay. Suppose for example, let's assume that theta is 30 degrees. So it can be any value. For time being, we will assume theta is 30 degrees. So if theta is 30 degrees at this instant, so this is the omega t, right? So at omega t equal to 0, sin minus theta is a negative value, right? So it will be a sine wave, something like. So the second expression is an exponential, and this will be a constant. It's 1 by 2 into t. Okay, we'll draw it with respect to. Yeah, so then it will be e power 0, right? So e power z, if you take, it will be 1 by 2 into 1. So it will be, we'll start from 1 by 2. It is starting from 1 by 2 and it's go on decaying. So at this instant, if you take, this is minus 1 by 2 and this is plus 1 by 2. So if we add these two waveforms, initially it will start from 0 and it keeps on increasing and then it keeps coming back. So this waveform, which is maximum, this actually it is not maximum at 5. It will be at some other angle. Earlier cases we have seen the current is maximum at 5, right? So this won't be maximum at 5. So this angle we call it as a beta. Okay. So we'll draw the same waveform in the earlier case. So this is nothing but I naught, right? So how the I naught looks here is I naught will start from 0. Not will be starting from 0. We start from 0, it goes here and it comes like this is called beta. So what is happening here? Till from 0 to beta, I naught is flowing, which means the switch is on. So when the switch is on, output voltage follows the input voltage, right? So it will be like this, and then it goes till beta, and then it becomes stops at beta. At beta, the switch is open, right? So output voltage will be, so we'll be having some negative peak here. Earlier cases, we don't have this negative peak. Right? Going.
Yes, yes, I understood. So we are
Yeah, yeah.
yeah,
It's till 1 o'clock. Yeah, anyway, I'll try to close it earlier on. Okay, it's almost done. Give me some 10 minutes. I'll be closed. Okay.
yeah,
So if you see, the major difference is the negative spike here.
yes,
So the next thing we have to do is that we have to find the average value of output voltage and the average value of the output current. Okay. So what is the average value of output voltage? Nothing but V naught. That is equal to, we have to take full cycle 1 by 2 pi integral 0 to beta, because the switch is conducting till beta, Vm sin omega t d omega. So this will come as Vm by 2 pi 1 minus cos beta. Got it? And similarly, I naught is nothing but V naught by R, because in steady state, the voltage, average voltage across inductor will always be 0. That's why we don't need to consider the drop across inductor. So that's why I naught is equal to V naught by R. And the one more term we have is the conduction angle, gamma SW. Here the switch is conducting till beta, right? So gamma SW will be beta. So now we'll see one example. After that, we'll close it. So what the question is? In a single phase half wave rectifier consisting R load of 50 ohms, is asking us to find the DC component of source current. So we have a, so this is a rectifier circuit. So we have a switch and then we have R load. So this current we call it as I out, right? Load current. Similarly, this current before the switch we call it as I source. This is the source current. What he's asking to find the DC component of source current. DC component is nothing but average value of the source current he wants. Suppose in this circuit, if you see clearly, there is only one switch, right? So I source is nothing but I out, because both are in the series, they are flowing in the same path. So the average value of source current is nothing but the average value of the load current. That is nothing but I naught, right? So which is equal to V naught by R. So we'll see that. So this is the R load, right? So if you take here in this case, the average value of I naught is nothing but V naught by R. So what is V naught? V naught we have seen right earlier. So it will conduct only for pi duration. So 1 by t integral 0 to pi Vp sin omega t d omega t. So how much we got? Going? Did you remember how much we got? Hello.
yeah. No, I don't remember.
Yeah, it's okay. It's okay. So, I'll do it. I'll do the derivation again. One second. Yeah. So it will be 1 by 2 pi. If you take Vp outside, integral sign is minus cos omega t, integral 0 to pi. So this will give 2. So 2 to get cancelled, we'll be getting Vp by pi, right? So I naught equal to V naught by R, that is nothing Vp by pi R. So what is Vp? Suppose a Vp is, suppose V source we call it as 50 sin omega. Then Vp is nothing but 50 pi 3.14 into R. R is 50. So we'll be getting 1 pi 0.14. Yeah. Is it clear? Is it clear, Gon? The sum? The example is
Yes,
clear?
yes, yes.
Yeah. Okay. So actually, and the next we will be having some conclusion, like what we have seen in this session. So first, we have seen some of the basic components of power electronics, like switches, switches classification, and RLC elements we have seen, right? So next we have seen the rectifier circuits and their classification, like single phase, three phase, controlled, uncontrolled, half wave, full wave. Yeah. And next we have seen a single phase half wave rectifier circuit, which will have source in series with one switch, and then we have a load. And we are seeing different loads here. We have seen R load, RL load, and the L load, right? If you recall, out of all these three loads, for which load the switch is conducting more time?
L L load.
Yeah, for R load, the switch is conducting for phi. RL load it is conducting till beta, which is greater than phi, but less than 2 pi. And for L load, it is conducting till 2 pi, right? So from this
Yes.
what we can understand is when the load inductance is increasing, the conduction angle. And the next point, yeah, that's it. These are the
Okay.
major topics that we have seen in this session. So, yeah, so do we have any doubts or is it clear?
Yeah, it's clear.
Okay, so maybe this is just a demo class. So if you have any doubts, you can come up. Maybe you can ask Dinesh and he will get in touch with me. Somehow we can manage. Okay. Yeah. Okay. Yeah. Thank you.
Hello, sir.
Yes, sir.
Yeah, done.
Yes, sir. We are done, sir.
Okay, thanks, sir. Thanks. So, Govind, how
Thanks.
is it?
Thank you, sir. Yeah,
Yeah,
it's good.
thanks.
Yeah, it's good. It's good. But there
Okay.
is some problem with me, so I have to study some more. Actually,
Yeah,
I will
yeah,
care
sure.
to
Yeah,
videos.
yeah,
Yeah,
yeah, sure,
but
sure.
the teaching was very good.
Thank you, thank you. So, lecture is good?
Yes, 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 very good.
Yeah. Oh, okay, thanks a lot for this because we are not worried about number of students. We always focus on best quality. You can check with Ram Shankar sir. Okay,
Yeah, yeah,
we are
quality is
happy
very
to,
good. But no doubt
yeah.
in there.
Yeah, and you will also see the less number of people. I am fine. We want to teach less but sincere students and those who really value learning. Okay, sir. Okay, yeah.
Yes, sir.
Thanks, Ramashankar sir, and you did a very good job, sir. And since you are teaching even first time on this online platform, I am very happy, sir. Thanks, sir.
Okay. Okay.
Thanks, Govind. Thanks.